next thing that we can ask is, what is the basis for this vector space? And that's actually quite non-trivial because, I mean, what is in P3? P3 is like, this is like ax cubed plus bx squared plus cx plus d with a, b, c, d in the base field, the scalar field. I think people call this ground field. So I'm actually confounding two different topics here. I'm talking like a physicist or engineer, where field means like values in space, like vector field, scalar field, but then the word field has a different meaning in math, which is about some algebraic structure here. So this R or C is called a ground field. But anyways, if we limit ourselves to real vector spaces, then this is what we have. And for this one, it's kind of easy to see what this vector space is like. It's really just 4 numbers, right? Right. So you have, this is like isomorphic to R4, which consists of A, B, C, D. Right? This is R4, right? And therefore there's a rather natural basis. What basis would you make for this space? What will be the basis for P3? Basis, I can use 1x, x squared, and x cubed. Right? That's going to span any element in here. And of course, these won't be linearly dependent. It's a linearly dependent set, right? So definitely, this is a basis for that one. So that's rather easy. But let's try to pose this question. What is a basis for U? Now I can't say the basis because if you have one basis, there's always other bases you can come up with. The only vector space that has a unique basis will be the 0 vector space. Yeah. Trivial? The trivial vector space. Yeah. In all the other cases, you have many different possible bases. But here the question is, can you find one basis for U? The trouble is that it has to satisfy this. So let's try to tackle this question. What is a basis for U? Can you come up with a basis for U? And the idea is to just plug this in here, see what it says. Okay, so if P of x is equal to ax cubed plus bx squared plus cx plus d, then what's P of 1?
A plus b plus
A
c.
plus b plus c plus d, right? What's P prime of 1? 3a x squared, 2b, and then you plug in 1, right? 2bx, and then you plug in 1, and c, and you plug in 1, right? So you have P of 1 and P prime of 1. All right? And we have the sum of those two, P of 1 plus P prime of 1. And that's going to be 4a plus 3b plus 2c plus d. And we are saying that this has to be 0. Oh, that's nice. That gives you a condition for this space. See, since this already has to be true, you can think of this as an equation for D and say D must equal to negative 4a minus 3b plus 2c. Now here's something interesting. Now we can say U contains all the polynomials of this form, where D has to be of this form. So what we just proved is that, therefore, any p of x in U must be of the form p of x equals to ax cubed plus bx squared plus cx, then minus 4a minus 3b minus 2c. Oh, made a mistake there. Okay? Now, does that reveal what the basis of this space is? This one kind of reveals some simple basis. Can you see it? Any ideas on how to get the basis from here?
Can you take the derivative?
No. I mean, we know that this polynomial is going to satisfy p of 1 plus p prime of 1 equals 0. So that's already done, because that's the condition that we got. Okay? If this is true, then this will be true. It's not a problem. What I want to do is I want to factor these two with a, and then factor these two with b, and factor these two with c. And now look, what do we have? We've managed to show that any polynomial in U is in the span of these three polynomials. Is that right? Because that's what span means. So this is in the span of x squared minus 4, x squared minus 3, x minus 2. These are your vectors. You know, these three vectors spanning the entire set. Now, question. What's the maximum possible dimension of U now?
Is it infinite?
No, it's spanned by three vectors.
Oh, 3?
3. It can't be more than 3, right? It can't be more than 3. And I think it is 3. Because, look, this is how you think. You have a vector space that's 4-dimensional. The original thing, P3 is 4-dimensional because it had A, B, C, D, right? And then you have one equation. So there's one condition. Every condition reduces the dimension by 1. So I think this should be giving you 3 dimensions. Okay? But how do you know for sure? Well, you know that for sure if you can show that these 3 vectors are linearly independent. Okay? Yeah. So now what we want to do is we want to show that claim x squared minus 4, x squared minus
4?
x cubed minus 4, thank you, x squared minus 3, x minus 2 is linearly independent. Okay? And now what you have is A times, well, linear independence means that if C1 times one vector plus C2 times another vector, C3 times x, the last vector, is equal to 0, we have to show that C1, C2, C3 is 0. That's the only way that you can have a 0. That's the definition of linear independence, right? But then if you write this out, this is like c1x cubed plus c2x squared plus c3x plus negative 4c1 minus 3c2 minus 2c3 equals to 0, but this is equal to 0 as a function. So you're really saying that this is equal to 0 as, I'm using triple equal signs because they're equal as functions, okay? 0x cubed plus 0x squared plus 0x plus 0, right? So it's equal to 0 as polynomials, which means that their coefficients should be the same. So we see that c1 must be 0, and c2 must be 0, and c3 must be 0 as well. So we've shown that the three vectors are linearly independent, right? See, x cubed has c1 as a coefficient, x cubed has 0 as a coefficient, they have to be the same. So what choice do you have but to say that c1 has to be 0, right? 0x squared, c2x squared, c2 has to be 0. c3x, 0x, c3 has to be 0, okay? So now you have that, and then we've shown that it's linearly independent. So if you look at what we just proved, we just proved that these three vectors span the entire space of U, and they're also linearly independent, and that's what a basis is, right? A basis is a set of a list of vectors where it spans the entire space, and it gives you linear independence if you try. Okay, so that's stuff. Okay, so the answer for the question I posed is that one example of a basis for this U is these three.